Well, welcome again. It's a great pleasure for me to present Gliia Braeyek.
Yeah.
She will talk about topology of Stokes complex related to a polynomial quadratic differential. It's the Université of Gabès?
Yeah.
Okay.
Okay. Thank you for this opportunity to be here. I will start with the motivation behind our problem. Alpha is a pole of the integrality trunqué F. The integrality trunqué is the solution of the first Painlevé equation with this asymptotic. If and only if there exists beta such that this Schrödinger equation admits a simultaneous solution with two different quantization conditions. We can find this in the paper of Kapeyev and in the paper of Masiro. Here psi is obtained by isomonodromic deformation. Also Masiro, in his paper, he proved that our Schrödinger equation admits in WKB approximation a simultaneous solution with two quantization condition only if the Stokes complex is of type Betrou. It means that in our Stokes graph, we have unbroken short trajectory, and I'm going to talk about this later. So I will take the cubic potential here, and I will take our quadratic differential associated to the Schrödinger equation. Without loss of generality, if we do an affine transformation, we may consider our differential is of this form. Of course, I will suppose that they have at least two different zeros of the differential. We obtain this if we do even a Mobius transformation because the Stokes graph did not change. Quadratic differential defines in a natural way a field of lines in the surface with singularity at the zeros and poles. The integral curve of this field is called trajectory of the differential. Is defined with this equation. With this symmetry, we can restrict our work for theta in this interval. The critical points of our quadratic differential are its zeros and pole. Here we have zeros 1, minus 1, and a. If you remember, our quadratic differential is defined with z minus 1 multiplied by z plus 1 multiplied with z minus a. A critical trajectory of a differential are the trajectory passes through critical points. Jenkins' theorem said that the set of the critical trajectory split the Riemann surface into 5 types of domain configuration. Here we have a polynomial, so the critical points are zeros and pole with a degree more than 5. So we have only 2 types of domain configuration, half-plane domains and strip domains. Here an example. If we take this cubic quadratic differential, you can see that we have only half-plane domains, and this is the critical graph and a strip domain. To get the Betrou case, we need unbroken short trajectory, no strip domains. So here I will introduce an equivalence relation. A and B are in relation if and only if the critical graph has the same structure. And the question is, when the data A and theta varies in the complex plane, how this affects in the Stokes geometry or in the Stokes graphs. The question is, if I get a short trajectory for which A and theta we have a short trajectory, we can answer to another question. If we take a polynomial p, for which, and the question is, if there exists theta such that this differential is very flat, it means that we have a minimum number of strip domains. How many of them when theta varies? To answer to these questions, we introduce this level set of harmonic function. Sorry, here a necessary condition of existence of short trajectory between two turning points is that the equation, the integral, imaginary part of the integral between the two turning points equals 0. So this is a necessary condition for the existence of short trajectory. For this, we introduce this level sets. Sigma 1 theta gives the necessary condition of existence of short trajectory between A and 1. Sigma minus theta between A and minus 1, also for sigma theta. And if we have an intersection between these sets, we have a necessary condition of existence of a true curve. We prove that this sets, sigma 1 theta and sigma minus 1 theta, are formed by three smooth curves, locally orthogonal in 1 and minus 1. The third curve starting from a real number, a positive number for sigma 1 theta, a negative number for sigma real number for sigma 1 theta, and a positive number for sigma 1 theta. And their direction to infinity are of the form minus 2 theta plus divided by 5 with k until 4. For sigma theta, it's a smooth curve starting from the segment minus 1, 1 and diverge to infinity with the direction pi minus 2 theta. This is an example of our level sets. The blue one gives the set of sigma 1 theta for theta equal pi divided by 4. The red one for sigma minus theta, the green one for sigma theta. Let's go back to our question. We have a necessary condition. We need the set when we have a short trajectory. A short trajectory appear. So I will define k theta is the set when we have at least a short trajectory. It means that the differential is very flat. I introduce this set. S1 theta is the set sigma 1 theta and is in the second intersection. And I take S minus 1 theta is the set sigma minus 1 theta. And the S theta is the set starting from the first intersection between the sets and goes to infinity. We prove that we have at least a short trajectory if and only if A is in the union of these sets. Also, the set k theta split the Riemann sphere into a finite number of connected domains where the structure of the trajectory have the same structure. There is no short trajectory. And any change of critical graph should pass by an appearance or disappearance of a short trajectory. Here an example for theta. Always we take theta at vary A. You can see when for theta equal this, when A varies, its effect in the Stokes graphs. If we are in omega A, there is no short trajectory. If we are in the red, there is short trajectory that lies minus 1 and A. Now we do a full classification of the Stokes graphs. If we are not in k theta, so we have no short trajectory. If we are in k theta, we have two types. The short trajectory could be in the boundary of a strip domain or no. And to pass from, we call it a type B. Here. Sorry. So. This is a type B when the short trajectory is in the boundary of strip domain, and this is a type BB when the short trajectory is not in the boundary. And to go from a type B to a type BB, we need to pass by a Botero case, unbroken short trajectory. And this is really important in our second part of this work. We use this classification, and we're going to see this after the break in the talk of Monder Shwichi, that we use this classification to study an inverse spectral problem with cubic potential, and to localize the zeros of eigenfunction associated to this cubic. It's in this paper submitted. So I said that to go from type B to type BB, we need to pass from a Botero case. So this is what we call a transition phase. We prove that if we are in the intersection, then we have a tree case. For theta in the interval 0 pi divided by 8, we have the intersection will be in 2 points, so we have two possibilities of Botero curve, Botero case. If we are in this interval, we have only one possibility of a tree case or a Botero case. This is for theta equal p divided by 4. We have some kind of symmetry here, so it's easier to work with this. And here the sets of E theta, the second intersection, and A theta. For theta varies in the interval 0 pi. For the green one is for theta in the interval 0 pi divided by 4, sorry. Here, another challenges, we still work to obtain the classification of the Stokes graph of quadratic differential when phi is a polynomial of higher degree or phi is a fractional function. And thank you. Congratulations, Frank, again.